Okay, so this is lecture 23rd. Let's go to our homework announcement first. So today we have homework number 18, and also you have 1 week. So it means that it's not that simple, and you have only one problem here. So now you have 2 files. The first file is named as homework 18.vertex, and the second one is named as homework 18.element. So your goal is solve the Laplace equation for a system described by these 2 files. These 2 files are invented to describe our complicated system. So it just looks like this. And using these two files, you can have information about our system. Then for this system, a user can specify 2 points for certain points and another certain point. For 1 point, the value of your solution is 1, and for a certain node, the second one, your solution should be 0. Of course, for all other points at boundaries, please use the homogeneous Neumann boundary condition. Simply speaking, you will have 2 files, and from these 2 files, take the information about your domain. Yes, this is your simulation domain, and user can specify 2 nodes, one node and another node, and for the first one, the solution should be 1, and second one, the solution should be 0. So solving the Laplace equation even in 2-dimensional case, that was already done in our course. But point is, now you have complicated domain, and that is described as many triangles. And for a collection of these triangles, please solve the Laplace equation. Please let me know all of you understand the goal of homework number 18. So now you have general file for describe a domain and take the information and solve the Laplace equation. For boundary nodes, so you apply homogeneous Neumann boundary condition and pick up 2 nodes and select 1 and select 0 for those 2 nodes. Okay, now you have 2 files. The first one is a vertex file, and the second one is the element file. So in this slide, it was already uploaded in our GitHub repository. So let me just give you the information. Okay. So can you see it clearly? Yeah. So this is your usual folder to find the PowerPoint files or PDF files. So you have plenty of PDF files devoted to our lecture contents. And at the end of this list, now you can find vertex file which was just uploaded 37 minutes ago and element file. So please take these two files to address your homework. And now just click our vertex file. So when you click vertex file, it contains many lines, almost 3,500 lines, and yes, it contains a lot of information. So handcraft manipulation is not available, so you have to make your computer code to understand this vertex information. So now you can clearly understand each line contains three numbers: the first number, and second number, and third one. So what is your guess for this information? Each line contains three numbers, three double precision numbers, and the file name is homework18.vertex. So now I guess that you may understand these three numbers are corresponding to x coordinate and y coordinate and z coordinate of your vertex. Here vertex means that a certain point inside our domain. Okay, so simply speaking, the first line, let me just write lead like this. So the first vertex point has the x points like minus 1.12. So you can see that this is corresponding to the first vertex has the x coordinate of minus 1.12 nanometer, and also its y coordinate is given by 5.78 nanometer. Of course, z coordinate is 0, and in this case we will just consider two-dimensional structure. So please neglect the third one, which is devoted to the z coordinate. Okay, so now let's go to the second line. Second line reveals that second vertex has the coordinate which is given by minus 1 point about 18 nanometer, and slightly go to the right position, and the y coordinate is same as before. They share the same point. And here you can see also another one. Here we have minus 1.18. This is the same as before, the same with the second vertex, and its y coordinate is almost twice larger than the previous one. So can you understand? If we just draw for vertex 1, 2, 3, then I would like to draw in this way. Let's just clear it. The vertex 1 and vertex 2 has located in more right position here, and yes, this is the vertex 3. Of course, here we have x coordinate and y coordinate. With this simple information, with these three lines, we can place three different points. Okay, then of course your first line, the first line just have the numbers which x coordinate which is exactly same with that of the first one, and y coordinate which is exactly same with that of third point. So you can easily understand the third or fourth point is actually corresponding to this node. Oh, that looks great. So okay, so up to now I have how to lead our vertex files. Oh, when you lead this file, although you have no information about the connectivity between points, but at least at the end of this file you may have such an information. So at the end of this procedure, now you can say you have many points: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After that you will have you will have yes, so many points inside your system. Here you have no idea are they connected or not, or are they connected or not. You have no idea about their connection, but at least you understand there are many points and every position is known to you. That is current situation only with vertex file. And then if you have understood everything, then why don't you go to the element file. So let me just show you our element file. Then let's go to homework 18.element. Then how does it look like? Oh, now you can find that there are again 3 numbers. Previously we had 3 numbers per line in vertex file, but in this case you have also 3 numbers, but seemingly it's like a natural number, so a positive integer, not a double precedent number. So what is your guess about these numbers? So number 2, 3, 7, or second element 1, 2, 3. So if we talk about the second line, second element, you can find that this is 1, 2, 3. What is your guess about 1, 2, 3? So you know that our number, our point 1, 2, 3 looks like this. It was 1, 2, 3, 4. And now in our homework 18.element, then we can find a line corresponding to 1, 2, 3. Then what is your guess about that? So maybe you can easily guess that this is really corresponding to a triangle which has 3 corner points: vertex 1, vertex 2, and vertex 3. So simply speaking, this one single line 1, 2, 3 means that we have an element like this. This is 1, 2, 3. So then why don't you go to another one? For example, here we have, for example, 1, 3, 4. How does it look like? 1, 3, 4. Then if we go to 1, 3, 4, this is simply saying that we have another element connecting 1, 3, 4 and coming back to 1 again. Oh, so now you can understand by reading all of these elements information. So how many? So there are more than almost 6,500 elements there, and okay, so you can have many elements, and now you can have many triangles connecting 3 points. For example, randomly select one. Yes, for example, this 18th line just to specify 18th triangle which connect vertex number 8, vertex number 9 and vertex number 11. 8, 9, 11. Then why don't you go to the vertex 8, 9, 11. 8, 9 and 11 are connected. 8, 9 has the same x position and y coordinate is different. So this is just when we try to connect number 8 and 9, we will have a vertical line. And here you can see that 11 has the same y coordinate with position number 8, point number 8, and x-axis or x coordinate is different. This is more slightly smaller in its absolute value. So let me just draw it. I guess that in this case we will have number 8, number 9, because so sorry about that, I cannot remember any longer. Okay, this is upper, number 8 is upper, and we have lower, and again here we have same y coordinate with number 8. So we will have things like this. We will have 11. So here, here, here we will have another triangle. I just randomly selected one of them, so you can try anything. So then you will have another triangle. Okay, so up to now I have explained or demonstrated how can we read the element file. There is no magic, but by just continuously read the vertex file and element file, you can access full information about this structure. Okay. Let me just wrap up the homework number 18. So each number is corresponding to the index of your vertex. And one more caution about this file. So this file is intentionally written in one based way. So it is not zero based system, but that is one based system. The first vertex is regarded as number 1 instead of number 0. So please be careful, especially you are not working with the MATLAB. Okay. Please remember that due is next Monday. And it means that I think that this is not that easy to you, because you have to internally calculate the so if you have certain triangle, you should calculate the lengths of your normal lines. So, and please use this line to calculate the flux calculation for your this and this element. So these two vertex points share single edge, and for this edge you have to use this vertical length for multiplying to your flux along this edge line. Okay. Today, at the first half of our today's lecture, I just explained our homework number 18. So it is closely related with unstructured grid. So if you can take the solution of that problem, then in principle you can treat any kind of two-dimensional unstructured grid. That's great, and that is a really big step forward. So please concentrate on this homework number 18. And now let me just start a discussion about slightly different topic in computational microelectronics. Actually, that is located at the boundary of computational microelectronics. So I think that our students group has two backgrounds. So one from ECS background and one from physics background. The reason why I draw the ECS in upper part and physics in lower part is because this is related with certain hierarchy. So when you go to the below direction, this is more fundamental and closely related with physics. And if we go to higher part, and that is more related with engineering, and that is more related with practical customer electronics. So up to now, we have discussed about many things related with exactly matched to this part. So if your major is semiconductor device, then maybe you have felt quite comfortable with our lecture contents. Of course, for some students from physics department, that is too much, how can I say, too much practical and too much engineering oriented. For unfortunately, lecture material in ahead is even more engineering related one. So we are now talking about this part. Of course, this is the entire one is the coverage over ECS, but here we have a little different one. So let's say that this is the coverage of semiconductor device research, and now we are talking about a certain field which is related with semiconductor circuit. So even you are measuring the semiconductor device, this part will be a little bit unfamiliar. So let's do it together with me. So however, we will quickly come back to this concept again. The reason why we are talking about the semiconductor circuit simulation, there is a twofold. One is, circuit simulation itself is actually at the border of our computational microelectronics. So, for example, our device simulation tool should provide the capability to perform the circuit simulation. That is practically required. And second reason why I'm talking about circuit simulation is this is best suitable to introduce the concept of transient simulation. Then once after talking about transient simulation with this circuit simulation contents, and we will come back to this semiconductor device and we will talk about how can we perform the transient simulation with the semiconductor device. Simply means that what will happen if we abruptly change the gate voltage or abruptly change the drain voltage, then what will happen to our semiconductor device? That will be discussed by this transient simulation. However, just to dive into the transient simulation in semiconductor device field, that will complicate our problem too much. So I'm afraid that actually most of you are getting bored or just left behind me. So that's the reason why we will work with much more simplified system like called semiconductor circuit. So electronic circuit. Actually, this is should be more frequently electronic circuit. Okay, but fortunately, if your background is physics, but circuit analysis is already taught in your general physics level. So I hope that most of you even come from physics department, you are familiar with Kirchhoff's law and the basic concept of this circuit analysis. That is my hope. Okay, so today's goal is an extremely simple problem. You have a resistor and you have a voltage source. For example, you have 1 kilo ohm and you have 3 volt, and your goal is to solve this system. What is the meaning of solve? So what is the exact thing we wanted to know? In this case, our most interest is laid on what is the current. What is the current flowing through the resistor? Of course, I guess that all of you can solve it by applying Ohm's law. Then you can easily identify the voltage across this resistor is 3 volt and resistance is 1 kilo ohm, and by applying Ohm's law you can find that I is voltage divided by resistor. So you have 3 volt and you have 1 kilo ohm. So you will have 3 milliampere. That will be your answer. I guess that, so to all of you, that seems trivial. But point is, how can we teach our computer to solve this problem? For example, we can apply Ohm's law. Yes, we can apply Ohm's law, but in order to apply Ohm's law, then we have to understand that so the voltage across the resistor should be 3 volt. But how can you understand this one? Of course, we can easily understand. Here we have 3 volt. Since this is 3 volt, of course, this voltage difference between two terminals of our resistor should be 3 volt. To us, that is quite intuitive and really easy to understand. But if you are on a computer and you say that this is 3 volt, yes, you can understand this is 3 volt, but it does not necessarily means that this R1 should be also biased with 3 volt. How can it recognize? We intuitively understand, oh, this one is identical and also this one is identical. So since we have 3 volt difference, still we have 3 volt difference. That is quite easy to understand, but for computer it is not that straightforward. So that's the reason why we have to a general way to construct our system for analyzing the circuit. So of course this example is easy to solve by us. However, if we slightly more resistors in this circuit, then it becomes more complicated for us to solve. Okay? So we wanted to make an automated way to solve circuit problems. So that is our motivation. For that purpose, we have to identify the general rule for governing this circuit. So that will be explained in here. Before introducing that general rule, we have to talk about the concepts inside it. If we have a circuit, then first of all we will define elements. So elements just represents something like resistors, capacitors, inductors, transistors, diodes, any of the components we will treat as a certain, how can I say, certain chip or certain something which can be bought in your electronic parts shop, that will be regarded as elements. For example, in this simple example in our lecture, what will be the elements? In this case, we will say that we have 2 elements. One is a voltage source, another one is a resistor. So also current source can be an element. Okay? So circuit is made by connecting the elements. So it is very similar like our previous understanding about specifying the domain. previously what happened? We just specified vertex points. We have vertex points by our dot vertex file. After that, what happens? We just specify their connection by specified in element file. So there are players called vertex or vertices, and they are connected. Yes, we have made connection. Yes, they are connected. So quite similarly, you have a voltage source, you have a resistor. It does not give you a circuit. Simply speaking, it's just like a situation like this. Only when you connect them, then you will have fully valid mesh. So quite similarly, you have elements here, and they should be connected to construct our circuit. So then yes and yes, that will be the connection between elements. So understanding element is quite simple. So now you can easily understand this concept. And one difference is vertex can have many edges. How many edges? It really depends on the situation. If you have more connecting edges, it's okay. Also, you can have many edges. You can have many edges. So the number of the edges which is belonging to a certain vertex is unlimited. So you can specify edges you wanted to have. However, your circuit elements are not free like the vertex. It has given numbers for connection. For example, how many connections are available for this voltage source? It has only 2 terminals for connection. How about this resistor? Also, it has only 2 terminals for connection. Then is every element 2 terminal? Of course not. So for example, you have solved a MOSFET for your homework number 17. Here you have source, drain, and gate. This is your source, and this is your drain, and this is your gate. It simply means that circuit elements can have 2 terminals. Yes, many of them have 2 terminals. Or some of them can have 3 terminals. Or some of them can have 4 terminals, 5 terminals. Any number of terminals is allowed depending on the physical implementation of your circuit element. So that is given number for each element. If you are working with a transistor, then you will have 3 or 4 terminals. If you are working with a resistor, then you will have 2 terminals. Then how about their connection? So connection is given by yes, this way. Here you have one element and another element, and they are connected. But you can think about these two different cases. Although VA and R1 is connected, but these two are completely different situation. Minus plus is connected. Sorry about that. Minus plus is connected. Then what will happen? Yes, this one and this one are not the same case in general. So simply speaking, it is not enough to specify VA and R1 are connected. Okay, it sounds great. However, it is not sufficient to fully identify the connectivity. Then how can you do that? So it is more reasonable to say like this. The positive terminal of VA and the positive terminal of R1 are connected. That would be much more specific, and that is enough to identify this connection without any ambiguity. So that's the reason why now we define a certain thing called a circuit node. Okay, here we have a node, but please note that this node is sometimes used in the device simulation as something like a vertex node, blah blah blah. If we are working with a semiconductor device simulation, maybe node is corresponding to a certain vertex. However, if we are talking about circuit, then this node is corresponding to a connection between multiple element terminals. Of course, we can find something like this here. Oh, sorry about that. Let's think about these points where multiple resistors are connected at the same time. Okay, this one also can be a circuit node, and here at this node we have many 1, 2, 3, 4 connected terminals. I think that this concept is quite easy to understand, but anyway, we have clearly distinguished the circuit elements and their connection nodes. Okay. One thing we have to cover in this lecture is once again convention for current, but that is hopefully that is already covered in our device simulation part. So consistently with the semiconductor device, so even in this circuit simulation, always the current incoming through the element is regarded as positive current. So say here we have voltage source and resistor, and say we have 3 volt here. This is a negative and positive terminal, and say 1 kilo ohm. Then of course we will have we will have 3 milliampere. Then my question is, how about the terminal currents of each element? You know that we have 2 elements and each of them has 2 terminals. Therefore, we can define 4 different terminal currents. Okay, for voltage source, we can define 2 different terminal currents. For its positive plus terminal and minus terminal. And even for resistor, we can define the terminal current for this terminal and this lower terminal. And let's say that we have 3 milliampere in this direction. Then what will happen to our terminal values? So can you say clearly? So since this is the positive direction for this positive terminal, however, terminal current flows in this way. So we have to say for this positive terminal of our voltage source, that should be minus 3 milliampere and go to this way. And yes, in this case, from the viewpoint of this upper terminal, then we can say this is 3 milliampere. But if we go to the lower terminal of our resistor, then what will happen? Although its positive direction is defined as this direction, but the current is actually the opposite way. So we have to say for lower terminal of our resistor, the terminal current should be minus 3 ampere. And we have this current, and yes, for negative terminal of our voltage source, it is aligned with the current direction. So we will have positive 3 milliampere. So at the first glance, you feel that a little bit confused. Why he is talking about 4 different terminal currents? Practically, there is only one circulating current and its direction is given. You know, this is just one single physical phenomena. However, we are now talking about not circulating current, but terminal current. The current seen from or measured from each terminal. So although there is one single loop of current, but depending on the observation point, that can be sometimes positive or that can be sometimes negative. Please understand these 2 differences. Okay, I will wrap up today's lecture. So, simply speaking, let's just summarize my today's talk. At the first half, we have discussed about homework number 18. At the time, we have introduced 2 different file format. One is vertex file format and one is element file format. So, together with the vertex file format, the element file specifies every element inside your domain. So my question was, or my homework was, to solve the Laplace equation by using those two files. That was the first half. And let's go to the second half. In the second half, we just review the concept of circuit elements and circuit nodes. And elements and nodes are player and their connections. So that was the main message of today's talk. In homework 18, you have to solve Laplace equation. So goal is to show your solution, for example, phi, so which satisfy the Laplace equation. That's the goal. However, when we talk about Laplace equation, solution of Laplace equation, we have to think about boundary condition. Boundary condition. Boundary condition. So in most cases, just to consider homogeneous Neumann boundary condition. Please apply homogeneous boundary condition. Instead, select two nodes, and for that node, instead of applying the Laplace equation, just to say that at that point phi equal to 1, and for another point phi equal to 0. So for example, let's go to our domain. You will have this this domain. Then specify any number for your 2 points. For example, you select this point and this point for your 1 and 0. Then you will have number 1 for your solution phi and number 0 for your solution phi, because you have specified that way. And for all other points like this one, this one, this one, you will have the solution of the Laplace equation. And of course, for these boundaries, you have to specify the boundary conditions, and the suggested boundary condition is just homogeneous Neumann boundary condition. Thank you, and see you this Wednesday. Bye.